You all know me. You know I love polyhedrons. Well, the other day I learned something new that I didn't previously realize about a wonderful alignment in how you can arrange. I mean, check it out. Here it is, right? Look at how you can arrange polyhedrons, polyhedra, your choice. And it's not just theoretical. Someone actually did it. Isn't that absolutely incredible? So I want to share with you this amazing new polyhedron plane. Quick, any other business? I'm doing unnecessary detail in Bristol, UK on the 12th of March. Come and say hi. And applications for Jane Street's Academy of Math and Programming are now open. More details about that at the end of the video. My journey of discovery started when my mate Glenn Whitney and some of his colleagues came up with an idea where people could send in polyhedrons that they would then display in an art installation. Of course, I wanted to get involved, but I thought I would include all of you. So I did a live stream, this is a couple months ago, where viewers watching it helped me work out what polyhedron I was going to build.
Hey, hello. So welcome to me on my second channel. I'm here to build a shape. Okay, well let's just start chucking these together. Otherwise, I'm never going to eat. Why don't we just make the tetrahedron? Come on, focus. Okay, I'm calling it. This is the shape. We're done. That's it there. I'm sorry, the autofocus doesn't seem to be cooperating. There it is in focus. Look at that. 3 blue, 1 gold. It's the tetrahedron we all didn't know we needed. It'll be in New Jersey, mid-April. Check out the plane website. Those are linked in the description. And go and marvel at this mighty polyhedron.
Glenn and friends took all the shapes people posted in and decided to hang them in a massive cuboid, which means they had 3 decisions for every shape, because there's 3 dimensions, 3 axes. There's 3 different ways they can adjust the location of any one polyhedron they're going to hang. And I've got a simulation here of some of the choices they could have made. This is a GeoGebra file that my friend Ben very kindly made for me. There's the empty cuboid waiting to have some shapes hung in it. In fact, I'll turn on tetrahedron. There we are. There's mine. Look at that. I mean, I'm not necessarily going to put it there. I just thought I'd show you. There's one there. In fact, we'll turn on the rest. We got a cube, we got an octahedron, and we got the rest of these. To start with, these are in not, any particular arrangement. They're just kind of lined up, ready to go. We got a few prisms. We got these are like dual pyramids back to back, and we got our friends of platonic solids and a square base pyramid. Why not? They're all set to go. So let's make one choice. Let's put them with, this is the number of faces on one axis over here. This is the total volume for a unit side length over there. And then this axis is vertices on big face. So that's why this octagon prism is all the way out here by itself. It's got the face with the most vertices on it. Whereas anything made from triangles, with triangles the biggest or the most complex shape, that appears over here like that. And so that's one way to arrange them. And I don't know, I guess you can kind of see some things coming out. There's not obvious patterns. Let's switch to another one. This is edges on one edge. This is the number of edges on this edge. Haha. Total surface area on this axis, and then the radius of the circumsphere on the third axis. And what can we see now? I mean, there's some in, like, obviously, okay, so surface area. This has got a lot of surface area for the volume it contains. Well, this is well, the radius of the circumsphere is not quite volume. Maybe we should have done volume. Anyway, so Ben Sparks, who made this, we had a chat about different ways we could put things on the various axes to see what kind of patterns we would see. But once again, they're kind of all over the place. So let's switch to something nice and simple. This is number of vertices on one axis, number of edges on another, number of faces on the third. And so now if we have a little look at these, we go, oh, wait a minute. They all line up. Look at that. So now they perfectly align in a single flat plane. I can actually turn on that plane. There you are. So they're all, look at that. They're all in that one flat plane. Isn't that absolutely incredible? And this is just for the ones that Ben and I put in as an example. So the question now is, if you take all the random polyhedra sent in by people to Glenn, and you hang all of them according to number of faces, number of vertices, number of edges in 3D space, will you get this fantastic plane? The only way to find out is to see the installation. And amazingly, I was able to see Glenn's math installation. Yes, math, because it and I happen to be at the same conference. So just up here, the joint math meeting is happening in San Francisco, USA. They have installed it in the main exhibition space. The installation now involves hanging all of these shapes in a very specific way. I'm so excited to show you this. I'm going to head up, see if I can find it. I was so excited walking across the main exhibition floor, and in the distance I could see a lot of very colorful, very chaotic shapes all suspended inside a cuboid. Yes, this is the installation, noun, not verb, of all the shapes that had been sent in. And sure enough, if you look at it from just the right angle, they all line up on the one plane. Some of you may already realize why they all lie in that one plane. In fact, that was the whole point of the installation. It's called polyplane because all the polyhedra are in the same plane. Now, if you know why, that's fine, but I was still struck by the mathematical beauty of how a few different math concepts all knit together to make this incredible installation possible, starting with Euler's polyhedron formula, which says the number of vertices subtract the number of edges plus the number of faces for any polyhedron with no cheeky holes in it will always equal 2. And this seems like as good a time as any to actually prove that. The first fact we need is that any nice polyhedron can be projected down into a planar graph. So here I have the case for a cube. There's a cube floating above a plane, and we're projecting it down onto that plane. At the moment, this is not planar, which just means that there are lines crossing each other. So this edge goes through this edge in terms of its projection down to that flat surface. However, there's always somewhere you can put your projection point such that, there we are, such that now we have a planar graph. Absolutely nothing is crossing anywhere. And as far as we're concerned, mathematically, this cube is equivalent to this projection. And it works for more complicated shapes. Check out this octahedron. So you got way more faces. And again, we can move this around a bit until we get it somewhere like that. Is that done? Yeah, there we are. So that works too. So any shape can become a planar graph. To make our lives simple going forwards, we're going to use the graph from my tetrahedron, the 3 blue, 1 brown, as simple as it gets. Tetrahedron, and its graph there you got, well, there's still the 4 faces. There's the 1, 2, 3 faces, and the 4th face that would be underneath, if you imagine this is kind of looking down on it, is actually wrapped out. The outside becomes a face as well. So those are our 4 faces. You still see the 4 vertices. They're now the vertices of the graph, and all 6 edges are there as edges of the graph. And what we're trying to prove is if you take the number of vertices, subtract the number of edges, add the number of faces, you get 2. If you ever forget the order of those, they go up in increasing numbers of dimensions that the things exist in. So vertices are 0-dimensional points, then you go up to edges that are 1-dimensional lines, and then faces that are 2-dimensional polygons. And it works in higher dimensions as well. You continue that where you put them in the increasing number of dimensions for each component, and you alternate the subtract and add, but it equals either 2 or 0 based on, I think it's 2 or 0, based on if you're in an odd or an even dimension. But anyway, we're looking at 3D shapes projected down into 2D. And we're going to do our proof by initially ignoring the edges. I'm going to take them all out. Forget the whole graph. We're going to replace it with a much easier graph. This is what's called a spanning tree graph. So we're using graph instead of network because mathematicians. A tree graph is one with no cycles. So I'm going to fill in just 3 of the edges. And this is a tree graph because everything branches but never recombines, which means we have now only got one face. So because we have lost these other edges here, there's just this one single face, because if there are no cycles, it can't section off one face as a region distinct from the rest of the plane. So now we just have this one massive face. And if you think about a spanning tree graph, so spanning means it goes through every single vertex, we now definitely have one more vertex than edges. which I kind of think about it in terms of like a fence post thing. But you can imagine the way you'd grow this. You start with one initial vertex, and each time you add an edge to another one, you go up by one edge, you go up by one vertex. Another edge, another vertex, another edge, another vertex. However you want to think about it, convince yourself for a tree graph, there's always one more vertex than edge, which means up here, if you got vertices, vertices, subtract edges, you end up with one, because there's always one more vertex than edges. Then, if you want to add on the number of faces, well, there's one face. One single face, so add the face equals 2. So this is definitely true for our reduced case with a spanning tree graph. Now we need to get back to our whole shape, because that's what we want to prove this for. So we're going to add the edges back in one at a time. And each time we add an edge, obviously the number of edges is going to go up. But if you add an edge, you also add a face, because every edge we add sections off another region. We're always closing at least a cycle. So if you add in that first edge there, you've now got one extra face. So that means the number of edges has gone up, but at the same time the number of faces has gone up, and we're subtracting edges and we're adding faces. So we have to subtract off one more edge and add on one more face, which cancels out. And that's the case for all of them. We put on another edge over here, one more edge, one more face, cancels out. Even like if we're adding an internal edge, internal for this arrangement, we pop that in, one more face, one more edge, cancels out. We can rebuild the entire shape by adding in edges, and each time we add in one more edge, doesn't matter, because it also adds in one more face, and those cancel out. So I guess the nice fact you have to trust me on is that any graph from a polyhedron can be covered with a spanning tree. But if you're happy with all of that, we've now got a hand-wavy proof that Euler's polyhedron formula is indeed true. You'll always get 2. If you would like a nicer proof of that, a very, very old 3 blue, 1 brown video, one of the original ones, is a proof of this very thing, except Grant uses the concept of a dual graph. Some of you may be familiar with dual shapes, where you swap faces for vertices and vertices for faces. You can do the same thing with a graph. It's a really nice proof. I'll link to it below. Fine, we know Euler's thing works, and the numbers of vertices, edges, and faces on the 3 different axes are somehow linked. But why does that relationship between them give you a plane? For that, we have to look at the equation of a plane, and for that, we're going to start with the equation of a line. I have here the classic y equals mx plus c. You can replace m and c with whatever letters the country you did your formative education in happens to use. It doesn't matter. Please, you may argue about it in the comments. Knock yourself out. I'm quite curious which countries have which letters. But we've got m here for the gradient. So if I alter the m in the equation, it just tips the line around. And we've got c. So if I alter c, it's just the vertical, the y-intercept. And that's enough to get any possible line. By moving up and down the vertical intercept and changing the gradient, you can hit any line you want. But that's not the only way to write the equation of a line. Instead of having y on one side and x on the other side hanging out with a constant, why not put x and y on one side and put the constant on the other? So here I can flip the representation, and once again, huge thanks to Ben for making this for me. Now we've got a multiple of x plus a multiple of y equals some constant, which in this case we've set to 1. And still the multiple of y, if I move b around, that still changes the vertical intercept. But now it's actually, if I move the multiple around, in this case, it's the inverse of it, gives you the intercept. But it's exactly the same. I can choose where I want that to cross the vertical axis. And A is the other one. I can choose where it crosses the horizontal axis. So now instead of choosing one intercept and the gradient, I just choose both intercepts. And that still gives us every possible line. And this is what we do 1 dimension higher. Here we are in 3 dimensions. We've got a times x plus b times y plus c times z, and they equal a constant we've happened to call d. And we can move them around. So there's the a one. I can move around. That's the x-axis intercept. I can move around the y-axis intercept. And I can move around the z-axis intercept. And actually, if I turn on the graph, it's a plane. We've defined a plane by, if you have any 3 intercept points on the 3 orthogonal axes, that gives you the definition of a plane, and you can get any plane you want by moving A, B, and C. We've also given a slider for D. It just scales everything up and down. And so often you'll see different values for the constant instead of 1. But for any of those, you could divide through by that value through through A, B, and C to adjust the intercept points. So, it's equivalent. You only need 3 variables to define a plane. And that's exactly what's happened here. I love this installation so much because it gets to the heart of, for me, what mathematical beauty is, where seemingly unrelated things have the same logic and pattern behind them. In this case, you have Euler's characteristic, where the Euler polynomial formula tells you that the 3 things are linked by equaling a constant, and you've got the notion of the equation of a plane in 3D space, which is the same form. So if you set vertices, edges, and faces as the 3 dimensions of 3D space, you end up with the same form of an equation for a plane, so the shapes match the plane. Oh, it's so good. I love it so much. The big question, of course, is where is my shape? And because it is the tetrahedron with its mere 4 faces, 6 edges, and here it is, 4 vertices. It's right here, a little unceremoniously, in the corner. And now for this long of Grant Sanderson complaining about what constitutes an edge. Which one upsets you the most?
Easily this one, right?
Right.
Because
it's just the vertihedron there.
no, because you're supposed to I'm actually not sure how you're supposed to understand it. I think you're supposed to understand it that these are edges. So as opposed to what any natural
each little dodecahedron is an edge?
each dodecahedron is a point.
Right.
And then you think of those points being connected into
Ah,
an edge.
right.
So it's just, and so one, I suppose, is invited to ignore the giant number of holes in a topic which is usually all about counting the number of holes. And I suppose one is supposed to ignore the fact that you've got like an enormous number of faces and vertices and edges that should get it like way
Is
heck
the
out there.
argument that some of these are like frames?
Yeah.
Polyhedron.
Yeah. I think that's what they're going.
Like-
Because you have a very eclectic style on like how they're even made or what they're made of or how you're supposed to interpret the faces. And the eclectic nature is maybe artistically nice, but arguably pedagogically confusing if you're trying to, educate a small child about
The nature,
minus E plus F.
yeah.
Yeah. Because there's a lot of like, no, don't count this as a face.
That's not yeah.
But then you go to this one, you're like, no, but do count this as a face. Because this one was made by Alex, who,
It's part of the installation.
well, yeah, but because he's like a mathematician, and he like, he's like, what's the whole point of this, and what's the whole point of like Euler characteristic? He's like, what's more fun is to get something that's off the plane that you can count the holes and see that, and so he deliberately does that. I'm assuming.
You may have noticed some 3D printed shapes are way off to the side. Still on the plane, but nowhere near the other shapes. And that's because friend of the channel, Henry Segerman, thought it would be very funny to bend the rules as much as possible while still, strictly speaking, staying inside the rules.
Matt may think it's bending the rules, but to a topologist, this beach ball shape is a perfectly sensible polyhedron. There's a vertex at the top, a vertex at the bottom, and 9 different edges connecting them together, which isn't a problem unless you insist on straight lines. There are also 9 faces, each with only 2 sides, which again isn't a problem if you're a topologist. So there are 9 faces, 9 edges, and 2 vertices, and 2 minus 9 plus 9 is 2, as expected. This one is a tetrahedron, which would have Euler characteristic 2 as usual, except that I added a bunch of vertices along the edges. Those are the blob things. Every time you add a vertex, you also split an edge in 2, so both the vertices and the edges go up by 1, which never changes the Euler characteristic, so it's still 2.
As an aside, when Ben and I were putting together this GeoGebra file where everything is plotted according to vertices, faces, edges, we noticed not only does everything lie on this plane, which now I can label, there it is, the Euler's characteristic and the equation. Look at that, it's so good. Everything lines up so neatly. We then realized that the shapes are forming 2 straight lines, and that's because we could choose the ones we plotted, and we picked a bunch which were joules of each other. And I can put on, there's a central line here. So that middle line on it, I'm going to zoom in. Everything's going to break a little bit. So here's my tetrahedron is on that line. And and where we put the line through is a bit all over the place. The square base pyramid is on that line. And then the other ones form two separate lines that go off. And they're two different lines according to shapes that are duals of each other. So the dodecahedron and the icosahedron are duals, and they're opposite each other as you go out along. So we don't, I suspect it wouldn't take much working out or thinking about it to show exactly what's going on there, but it seems really nice that not only are the shapes all on the polyplane, but they're forming these two neat, like they've taken marching orders and they're partnering up with their dual shapes, and the self-duals are on the line. Maths. If you would like to see the polyplane installation in real life, it is no longer in San Francisco. Glenn packed it up the next day, put it into a van, drove away with it. It's now at UCLA in Los Angeles at the Institute of Pure and Applied Mathematics. It will be there for all of February from the 1st to the 28th. That's not quite all of it, is it? Not this year. Anyway, you can go and see it there if you're anywhere near Los Angeles. They're still accepting shapes. So if you want to build polyhedron, you can post it in. Details on polyplane.org. Yep, that's the website. I'll link to it below. And you can even apply to host it. If you're at a place or an institution or whatever who would like to have polyplane installed, you can get the details on the website for how to go about doing that. But up next, a word from the sponsor of this video, Jane Street, who are not trying to sell you something, they're trying to give you something. Jane Street are now accepting applications for their Academy of Math and Programming, which is a summer program, runs from the end of June through to the beginning of August in New York City, and it's a no-cost education program for recent high school graduates who are interested in math and computer science and have experienced some kind of barrier in their education thus far. If you get accepted onto the program, not only will Jane Street pay for your travel, food, boarding, program fees, the works, they will also give you $5,000 scholarship towards your future education. It's such a great opportunity. Applications will close on the 13th of March. So if you or anyone you know could benefit from this program, please do send them the link. I'll put it below. And Jane Street have put together a puzzle that you can try. This is not compulsory. In fact, anyone can do it. You've got to arrange numbers that represent skyscrapers on a grid, just to give you a taste of some of the type of content that will be involved. But it's way more than that. It will cover everything from mathematics to computer science, data analysis, game theory, and more. And you get to meet me, probably. I was there last time. I think I've been to all, well, the last two definitely. I'm hoping to be at the one at 2024. Such an incredible opportunity. Huge thanks to Jane Street for making this possible. Please do either apply or pass it on to someone who can apply. And thanks to Jane Street in general for sponsoring this channel. They were also at the joint math meeting. They ran an estimate-a-thon where people could get into teams and compete to estimate things in Fermi-style problems. And they put on an event for undergrads. They can go along, get a free lunch, listen to some staff from Jane Street talk. And from this guy, I popped by to say hi. Always very happy to meet people who may be considering applying to work at Jane Street. I think they're a great organization. They do financial things. So please do check out AMP and Jane Street in general. Links below. That's it. End of the video. Thank you. Watch to the very end of the video, gang. For you fine people, which is very much not everyone. Yeah, a bunch of post-it notes in the background. Finally finished writing my next book. You might find a link at the very bottom of the description where you can sign up to hear about pre-orders. It's the pre-orders.